In the last part of this introduction to cache lecture, let's look at some basic cache performance equations and basic factors that affect cache performance. As we have discussed previously, we have two concepts here. One is the miss rate, which refers to the percentage of accesses, of data accesses that are cache misses. And we have a concept called hit rate, which refers to the percentage of the data accesses that are cache hits. In the previous example, in the previous simple cache example, we know that we have 2 hits and 7 misses, and we have a total of 9 accesses. So the hit rate is 2 over 9, which is 22%. And the miss rate is then 7 over 9, which is 77.8%. Additionally, we also have an equation for computing average memory access time. And average memory access time is effectively a weighted average of the hit latency, how long it takes to do a hit and how long it takes to do a miss. So average memory access time is defined as hit latency, the latency of hit multiplied by the percentage of hits, so the rate of hit, plus the latency of miss multiplied by the percentage of miss. So we sum them together, it gives us the average memory access time, how long it takes to access the average memory latency for accessing a series of memory accesses, or the average time, or the weighted average time for each latency, how long it takes, the average time that it takes to do a memory access in the CPU. And because we know that actual miss latency is effectively the sum of the latency hit plus miss penalty, we can replace the latency miss with this equation. If you don't remember how do we derive this equation, you can go back to check the previous lectures on the cache latency and on the cache hit time and the miss time. So let's replace this miss latency with this equation. So what we're gonna have here is latency hit multiplied by rate hit plus the latency hit plus miss penalty multiplied by miss rate. And then if we break down this parenthesis, this box here, what we have is hit latency multiplied by rate hit ratio plus the latency of hit multiplied by miss rate plus the miss penalty multiplied by miss rate. And if we combine the first two terms here, take out the common coefficient, latency hit, combine the first two terms, we have if we combine the first two terms here, what we have is effectively latency hit multiplied by rate hit ratio plus the miss ratio. So we're gonna have latency heat multiplied by heat ratio plus miss ratio. And we know that actually for memory access, for cache access, is either heat or miss. So the sum of the rate ratio, heat ratio, and heat rate and miss rate is going to be 1. So if we replace this one with 1, we know that the sum of them has to be 1. Otherwise, we're going to violate the definition of heat-miss ratios. So we know for the first term here of this average memory access time is effectively just latency, miss latency, heat latency multiplied by 1, plus the miss penalty multiplied by miss rate. And consider the previous example. If the heat latency is 1 and miss penalty is 100 nanoseconds, what is the MAT for the previous example? So we know that, so if we plug in these numbers into this equation, we know that the heat latency is 1 nanosecond. So this is 1 nanosecond multiplied by 1 plus miss penalty, which is 100 nanoseconds. 100 nanoseconds multiplied by the miss rate that we have computed previously. And we know that the miss rate here is 77.8%. So multiplied by 77.8%, it gives us the average latency of 78.8 nanoseconds. And this 78.8 nanoseconds is the average memory access time for the previous example, for the 9 accesses that we did previously. And in general, in an application, the total execution time can be divided into 2 components. One part is the memory. One part is actually the computation time, the time that we spend to do the arithmetic operations, and the second part of the execution time is majorly composed of memory access time, the time that it takes for us to do memory accesses. And because the memory accesses are usually the memory time, usually are the time that actually the pipeline is stalled to wait for the data to be brought in from the main memory. So the time of total execution time can be further decomposed into the time for computation plus the time that the pipeline that is stalled, the pipeline stall cycles that are waiting for the data to be fetched from the main memory. And since the pipeline is usually only stalled if the data is brought in from the register, the pipeline is not stalled. And if the memory is brought in from level 1 cache, the CPU is usually not stalled as well, because level 1 cache is very fast. Therefore, all of the memory stalls usually corresponds to the cache misses in L1 cache. So the time for computation can be further approximate with the computation time, the cycle spent on doing arithmetic operations, and the time that it takes to serve cache misses. And the time that it takes to serve cache misses is effectively the latency, the miss latency, multiplied by the miss ratio. So once you know the time for computation, and once you know the miss latency, or the rate and the miss rate, you can compute the execution time. Or as in most of the time, that when you know the actual access time, the execution time, that if you measure the execution time, and you can measure the cache miss rate. If you know the cache miss latency, and you can measure the cache miss rate, then you can compute how much time it actually spends, the program spends to actually doing the computation. And also, for that, the previous equation is just a approximation. And for better accuracy, we have better accuracy of the previous equation, it is usually better to consider read and write accesses separately, so you do not have to. So you can actually have more accurate counting of the cycles. And strictly speaking, the time that when we talk about here, exec, is only the time on CPU execution. It does not include CPU execution. It does not include time for I/O wait or OS scheduling overhead. So the real execution time would be the time execution, CPU execution time plus the time that is the program spends on waiting for I/O, and the time it spends on waiting for the OS to schedule it to execute. There are also several factors going to affect the heat latency, mid latency, and miss rate. Miss latency is mostly dominated by the speed of the DRAM. So the faster DRAM, faster main memory is going to give us smaller miss latency, since it's faster to serve the miss. And this miss latency is also determined by the latency of the data path from CPU to DRAM. So the faster the data path is, then the smaller the miss latency is. Heat latency is mostly dominated by the latency of the data path from CPU to the cache. So if the data path is shorter and faster, then we're gonna have smaller heat latency. And heat latency is also dominated by the cache size, the size of the cache. Basically, larger cache will indicate to slower heat, because there are more cache lines, slower heat or longer heat latency, because if it's a larger cache, then there are more frames. There are more frames that we have to compare. Then we have more frames that we need to compare their tags, so that it takes longer to actually locate the piece of data in the cache. Therefore, the bigger the cache, the longer the heat latency is. And heat latency is also determined by how long it actually takes to compare the tags. The faster the tag comparison is, the smaller the heat latency is. Besides miss latency and heat latency, these two terms, one of the major cache optimization metric is cache miss rate. Or the goal is to reduce the cache miss rate as much as possible. Where actually the whole goal about designing all these cache placement policies and cache replacement policies and write policies is to reduce cache miss rate, to make sure that you have as many heat paths as possible and as fewer cache misses as possible. And unfortunately, optimizing the cache miss rate is usually contradicting the goal of reducing the miss latency and heat latency. So sometimes the optimization that reduce miss rates can actually increase cache latency. So there's also a trade-off between reducing the cache miss rate and reducing the latency of the cache, including the miss latency and heat latency.